Okay, scholars, let's begin discussing Newton's laws of motion. There are three of them, and they're going to be the foundation for everything that we're going to do in this portion of the unit. You're going to learn some very important skills, and in fact, the skills are more important than these definitions I'm giving you. Ultimately, you guys are going to be able to model forces and use a mathematical model to make predictions and solve problems. So, Newton's laws of motion. The first law. This law is also known as the law of inertia, as you'll see. This law says that an object resists changes in motion. Objects don't want to change their velocity. They don't want to accelerate. They tend to do just what they've always been doing. And we'll see in the next law what can actually cause a change in motion. Remember, that's the whole question that we are trying to address right now, is what causes an object to change its motion. Well, now we're seeing, first and foremost, that objects don't want to change their motion. Objects have a property known as inertia. And inertia is simply a measurement of that tendency to resist motion change, tendency to resist acceleration. It's also known as an object's mass. How massive an object is a measurement of its tendency to resist a change in motion. Let's say that you are the tragic figure from Greek mythology, Sisyphus, and you have been tasked for all eternity to roll a stone up a mountain. As soon as you get the stone up a mountain, it falls back down. You have to run back down, push it up again, over and over and over and over for all eternity. If you were Sisyphus and you were given a choice between which rock you would rather roll up the mountain, which one would you choose? I think we would all agree that we would much rather roll one of these tiny little pebbles up the mountain for all eternity as opposed to the big giant boulder. These little pebbles have very little mass, very little inertia, and so they're not going to resist changes in motion very much. They're going to be much easier for us to roll up the mountain. So, first law, very simply, which rock would you rather roll up the hill? The tiny one. It has less inertia. It tends to resist motion. It tends to resist changes in motion much less. Objects tend to resist changes in motion. Simple enough, pretty common sense, I think. In order to talk about Newton's second law, I'm going to take you through kind of an experiment and some data that was collected for this experiment. Now, you all should be getting pretty familiar with graphs right now. I want to give you a moment to look at this graph and notice what's on the axes. Whenever you're given a graph that you're unfamiliar with, maybe on an exam, a standardized exam, something like that, you should always look, first of all, at the title of the graph and then see what is on the axes of the graph. What is actually being graphed? What is the data? And then look for relationships between the variables. So I'm going to give you a moment to see if you can figure out what was being recorded, what was being experimented with this data. So you'll notice on the y-axis we have acceleration, meters per second, meters per second squared. On the x-axis we have what is known as the net force. Now I hope that you remember that in experiments we always have an independent variable and a dependent variable. The independent variable always, whenever we take data on it, we always graph it on the x-axis. So we can say that the independent variable is, this says net force. I'm going to simplify that for us just for the time being. As force. This says net force, so net force. We'll talk about what that means here in a bit. And the dependent variable, remember, that's the thing that you are hoping to change. You are asking yourself, how does the dependent variable change in response to the independent variable? How does the dependent variable depend upon the independent variable? The dependent variable is always graphed here on the vertical y-axis, and in this case it is acceleration. So these are the variables. So whoever was setting up this experiment, it looks to me like they took two sets of data. They took this green triangle set right here, and then they took a blue diamond set of data and graphed it here. So two sets of data, both of them show an interesting relationship. Do you notice a relationship between the variables? Yeah, this scatter plot seems to say that as the net force increases to the right, the acceleration also increases. We call that a direct relationship. These variables are directly related. Net force and acceleration are directly related. So this person was measuring a force, the net force on an object, maybe a little car or something on a little track. And then the person measured the acceleration. How did the acceleration change in response to the net force? And as the net force went up, the acceleration also went up. That is true for both of these sets of data. So we could say from this data, from this experiment, we've come to a conclusion that net force and acceleration are directly related. Net force and acceleration are directly related. They have a direct relationship. Remember, that means that as one goes up, the other one goes up. And we can notice that that relationship seems to be linear. Let's look at this. You'll notice that there is a linear equation here, y equals mx plus b. It's a straight line. They have their slope. They have their y-intercept, their b right here. That is actually incredibly tiny. Let me talk to you a little bit about what these numbers mean. 9.99 e negative 17. That e there, some of you may have seen it before on your calculators. 9.99 e negative 17. The e means times 10 to the power of, so times 10 to the power of negative 17. This is scientific notation. That means that this number is actually 0.00000 and then 16 total zeros, 999. That is incredibly small. So we could say that that b is practically 0. And it is also true for the other set of data, that the y-intercept here is also practically 0. That is 0.0 with 15 zeros and then a 2. So that's incredibly small. So both of these have y-intercepts that are about 0. Remember, the y-intercept is where the line crosses the y-axis when the x value is 0. So where does it hit when x is 0? Where does it cross the y-axis? Right here? Well, I think it makes sense. Think about what this data is. Net force and acceleration. If there is no net force on the object, the acceleration is going to be 0. That's what this is saying. So we can take this linear relationship and we can make it into a more useful mathematical model. We know it's linear, y equals mx plus b. We have just shown that that b value is 0. So we could say y equals mx. And we can replace these. The y value was what? Acceleration. The m is the slope. We'll leave that for now. And then the x value is net force. Let's use a capital F to represent that. So this is a mathematical model. If we know the slope right here, then for any given net force on an object, we can predict that object's resulting acceleration. And from this equation, you should be able to see that as force goes up, what would happen to acceleration? If you plug a larger number in here for force, this m value remains constant. It is one number, one slope. What's going to happen to the a value? It's going to go up as well. These are directly related. If you increase the f on this side, m times f, you're going to get a bigger number. So this does indeed show us that net force and acceleration are directly related. Let's keep that in mind, and let's look at another set of data.
Why are you talking to it?
Well, it's recording my voice. I'm going to say hi.
Hi.
You want to tell them your name? No? Okay. Hero, do you want to tell them your name? Bark, bark, ruff, ruff. All right, boys.
Hello.
Let Daddy do his work. Henry, please. Okay, I want you guys to look at this data. Notice we once again have two different sets of data. It's a little bit more difficult to see here, but we have these blue dots, and then we have these triangles, and use the same method that we did last time. Think about what experiment the person could be doing this time. I'll give you a hint. They are still measuring acceleration of a cart, a little tiny car, and this time they're changing something else. So I'll give you a moment to see if you can figure that out. So the independent variable of this experiment is what? It's the mass, right? they are changing the mass of the cart each time. You can see right here the mass is about 0.25 kilograms, 0.5 kilograms, 0.75, 1, 1.25, 1.5. So they must be adding little weights, little masses, little pieces of metal or something to the cart to make it more massive each time. And then they're getting that cart to accelerate. They're getting it to change its motion, and they're measuring the acceleration. That's the dependent variable. How does the acceleration depend upon the mass? What sort of relationship do you see here? We can say that as the mass increases, what happens to the resulting acceleration of the cart? You guys already know this. We've already discussed this. A heavier cart, the most massive object, is going to be more difficult to move. It's going to have the smallest acceleration. The least massive object, right here, is going to have the largest acceleration. We've already talked about that. That's the idea of inertia, right? Objects tend to resist accelerating. They tend to resist changes in motion because of their inertia, because of their mass. So the more massive objects result in a lower resulting acceleration when a force is applied. In experiment 1, we said that acceleration is directly proportional to the net force. As the force goes up, the resulting acceleration goes up. And now in the second experiment, we're saying that the resulting acceleration is inversely or indirectly proportional to what? The mass. So we have two different relationships here. As the net force on an object goes up, you increase the force, you're going to increase the object's change in motion, its acceleration. But then we also know that if you increase the mass of the object, then that's going to result in an object that has more inertia, resists changes in motion, resists acceleration more, and so it has a lower acceleration. That's what it means to be directly proportional and inversely proportional. Direct proportionality means one goes up, the other goes up. Inverse proportionality means one goes up, the other one goes down. So from this data, which you should be able to kind of think through just looking at these graphs, from this data, we can get Isaac Newton's second law, which is right here. This one is pretty hefty, so let's walk through it step by step. This law says that in order for an object to change its motion, remember, that's the whole question of this unit. What does it take for an object to change its motion? How is it that objects can speed up, that objects can slow down? Well, now we've answered the question. We know that objects tend to resist this. That's inertia. And so in order to overcome the inertia, in order to set an object speeding up or slowing down, to change its motion, to give it acceleration, there has to be a net external force. It is very important that you get these words down. Net external force. Let's define, first of all, what a force is. We've kind of been throwing this word around. Let's define it now. A force I'm defining here is a push or a pull that has the potential to cause a change in the motion of an object. In other words, it has the potential to accelerate an object. This word external here means that it must be coming from another object. It must be a push or a pull from something else. And this word net here means total or overall. I'll write that right here. Another way of saying that, which we'll discuss in a minute, is unbalanced. There must be unbalanced forces acting on the object in order for it to change. So, in order to overcome inertia, we need a net external force, a total overall unbalanced push or pull that's coming from the outside. The resulting acceleration, which we've seen in those experiments, is directly proportional to the size of the net force. The resulting acceleration is indirectly proportional to the object's inertia or mass. So once again, if the mass goes up, then the acceleration will be smaller. Isaac Newton formalized all of this in one very important equation. It is the second law equation, and it is this.